If I had to summarize my research in one sentence, I work as part of a group to detect planets around young sun-like stars with the end goal of furthering our understanding of how planets form, how they evolve, and ultimately how we got here. Now, those are all questions that would have been much more difficult to answer 30 years ago, when our observational basis for planetary science was really limited. Planetary isn't like big picture planetary, not like geology. Step on this. Was really just the solar system, as in we had a sample size of 8. Well, back then it was 9, there was Pluto. But in the 90s, astronomers began to detect planets outside of the solar system, around other stars, called exoplanets. And as of today, we have discovered 3,826 planets around worlds, or stars other than the sun. So our sample size has gone up a lot. And we haven't just discovered a lot of planets, we've discovered a wide variety of planets. We've discovered planets that orbit their star at 1/1000th the distance that the Earth orbits around the sun. Planets that orbit at hundreds of times the distance the Earth orbits around the sun. Planets that orbit their star in the time that it would take you to eat a meal at a restaurant. And planets that have barely gone around their star in the time since the last crusade. The war, not the movie. With all these observations, a lot of which are planets that are so much unlike what we would expect from just our own solar system. Theories of how planets form and evolve have really developed over the last couple decades. Which is to say that while we've gotten a lot better at understanding some aspects of it, there are other topics that we didn't even consider before that are now lively debates. One thing that all theories do agree on is that planets form in disks around stars. These disks are the leftovers of the nebula that originally collapsed to form the star itself. How planets form within these disks is more up for debate. There are two main theories: core accretion and gravitational instability. In core accretion, small, very small dust grains in the disk collide and stick together, clump up, and then gravitationally attract other clumps, and in this way get bigger and bigger and build up at the beginnings of the planet. In gravitational instability, a region of the disk is inherently unstable and just collapses all of a sudden at the beginnings of the planet. Now, both these theories are probably true. Some planets form through one of these processes, others through the other. What we don't have down as much is what sorts of planets form through which of these processes, how often, and why. And furthermore, there are some planets that we've discovered that can't be explained as they are through just being formed through one of these processes, but also need something to have happened to them after they were formed through one of these processes, some extra step in their life cycle. And this extra step is called planet migration. I don't mean this sort of planet migration, which is what can come up on Google when you look up planet migration. That says no passport required. No, I mean this sort of planet migration in which the planet interacts with the disk around it such that it moves. And despite how important this process is for shaping planetary systems, it's very physically complicated to the extent that if we want our models to be at all accurate, we need more observational constraints than what we have. What we have right now is mainly just that migration needs to occur fast enough that it's done by the time the disk goes away on its own, which happens in about 10 million years. But not so fast that it has runaway effect and just sends the planet into the star. Now, one of our best ways to constrain all these things I've been talking about and develop our theories of them, planet migration, gravitational stability, core accretion, all this stuff, is to detect planets around stars that are so young that they still have their disks. That's what my research tries to do. Because so soon after formation, these planets, just by our direct observations of them, we can tell whether or not they were formed through core accretion or gravitational instability, and then we can extend that knowledge to how these processes work in general. At the same time, just knowing at what distances and ages we see planets at all around stars so early in their lifetime tells us a lot about how migration works and how fast it happens. So these stars that still have their disks that I look for planets around in my research are called classical T-Tauri stars. They're basically baby suns. The sun was once a star like this, and Earth once lived in a disk like this. So the methods I mainly use to detect these planets are the transit method, in which you look for a dimming of the star periodically as a result of the planet eclipsing in front of it in its orbit, and the radial velocity method, in which you look for changes in the brightness of the Earth, not brightness, but the light coming from the star as a result of gravitational effect of the planet working around it. Now, the bad news is that both these methods, while tried and true and the workhorses for discovering those 4,000-ish planets that I put up here earlier, they're very hard to apply to classical T-Tauri stars, because classical T-Tauri stars are young and adolescent and do things, and they mimic these signals naturally that planets would put out. So the good news, though, is that just a couple years ago, my advisor here at Rice, Professor Christopher Johns-Krull, led a collaboration that discovered the first planet around a classical T-Tauri star. So this is great because it shows that our methods can indeed discover planets around such stars, and now we just need to increase our sample size so that we can draw stronger and wider conclusions on how this affects our theory so far. For me, for my part, that's meant looking through transit data to try and find planet candidates. And I have found a couple that look promising, and while we wait to follow up on those to confirm whether or not there truly are planets around them, I'm doing radial velocity analysis of another star that looks like there's definitely something going on there. So in general, a lot of irons in the fire right now. We've thrown out our net. We'll see what we catch. Thank you.